Welcome to this explainer. If you've been tracking AI workflows, you know the landscape is shifting at lightning speed. Today, we are cracking open LangGraph Module 4, and let me tell you, the advanced multi-agent capabilities they've just dropped are absolutely mind-blowing. We're talking about edgeless workflows and parallel agents that completely rewrite the playbook on how we orchestrate complex AI systems. So, let's jump right in.
We really need to start with the massive elephant in the room. How on earth do you control multiple AI agents without manually hard-coding every single conceivable path they might take? If you've ever tried building a multi-agent system, you know this is a huge bottleneck. Sure, defining every turn works for simple toy apps, but the second you want a genuinely intelligent, dynamic system, one that actually reacts and routes itself, that traditional hard-coded logic just hits a massive brick wall. So here's our roadmap for the explainer today. We're going to cover the jump to advanced LangGraph, unpack the new dynamic command tool, look at updating state on the fly, dive into parallelization and fan-out, learn how to tame data chaos using custom reducers, and finally, put it all together with a real-world multi-agent search build.
All right, let's kick things off with a welcome to advanced LangGraph. Moving right along to our second topic, the dynamic command tool.
Up until now, developers basically had to act like total micromanagers. Think of the old conditional edges like laying down rigid train tracks. You literally had to place every piece of steel yourself. A node runs, a routing function evaluates a condition, and pushes the workflow down a strict, predefined path. But the new command tool? It's like upgrading to an intelligent dispatcher. Instead of writing endless, clunky conditional logic, your agent simply fires off a command saying, hey, here's exactly where I need to go next.
The absolute game changer here is that you no longer have to explicitly define those edges beforehand. You're giving the AI agent the power to decide its own destination. This is what we mean by an edgeless graph. Instead of hardwiring lines between node A, node B, and node C in your code, you just hand the LLM the available options. And incredibly, it evaluates the user's query and routes itself entirely on the fly. It is just so much more fluid.
Which brings us to part 3, updating state on the fly.
Now, dynamic routing is awesome, but what about the data actually flowing through these workflows? And AI is really only as smart as its state, its memory. In the older architecture, if you wanted to update the state, like grabbing a user's profile, you usually needed a completely separate step just for that, before you could even think about routing. But with the command tool, you can do both at the exact same time. Your agent issues a single command that updates the data, say logging the user's name as Amin Alam, and instantly jumps to the next node.
You honestly won't believe how much cleaner this makes your code base. You're combining complex decision-making and memory updates into one fluid action. Imagine a user logging in. The first node can verify their ID, inject their personalized data right into the state, and immediately route them to a specialized agent. All of that happens in just one line of code. It's incredibly efficient.
Okay, let's level up again with section 4, parallelization and fan-out.
So, what if your AI needs to juggle a few things at once? Sequential processing, doing task A, waiting, then task B, waiting, then task C, is just way too slow when those tasks don't actually depend on each other. To fix this, we use two concepts, fan-out and fan-in. Fan-out is when you distribute tasks to multiple parallel agents simultaneously, and fan-in is simply waiting for all those parallel agents to finish up and report back to a single point. Think of a manager handing out research assignments to a team of analysts and then waiting at their desk for everyone to bring back their reports before making a final call. That's fan-out and fan-in a nutshell.
And the beauty of this new command tool is that it makes parallelization trivially easy. Just pass a list of agents to the go-to parameter and boom, you trigger a fan-out. Let's say the AI decides a user's question needs both real-time web data and historical context. It just issues a command with a list like go-to equals search web, search Wikipedia. Without changing your core graph architecture at all, both of those agents fire off and run at the exact same time.
But with great power comes a little chaos, bringing us to section 5, taming chaos with custom reducers.
Because here's the thing, parallel processing introduces a massive, often hidden danger. Ask yourself, what exactly happens when two parallel agents try to write to the state at the exact same millisecond? Without some sort of traffic control, this essentially causes a massive multi-car pileup in your code. It'll crash your system because the state key typically can only receive one single value per step.
The fix for this is something called a reducer. A reducer is basically a function that dictates exactly how your graph should combine new incoming data with the existing data. A standard reducer avoids the crash by appending the data instead of overwriting it, basically forming a nice little queue. But that creates a brand new headache: chaotic output order. Because your agents are running in parallel, Agent C might finish its job faster than Agent B. Suddenly, your beautifully structured data looks like a randomized mess.
When you compare a standard reducer to a custom sorting reducer, the difference is night and day. A standard reducer just tosses data onto the pile as it arrives. You get a totally unpredictable order based purely on execution speed. But by writing a custom sorting reducer using standard left and right logic in Python, you get to dictate the exact structure. You can enforce a strict rule that, no matter who finishes the race first, Agent B's data will always appear before Agent C's data in the final list. It completely tames the chaos, forcing those parallel outputs into a clean, highly predictable sequence every single time.
All right, let's tie it all together in Section 6, Real-World Multi-Agent Search.
Let's take all this awesome theory and apply it to a real-world prototype to see how it drastically improves accuracy. By combining parallel fan-out and fan-in, we can actually build an AI search engine that cross-references multiple sources simultaneously. Imagine a user queries NVIDIA Q2 2024 earnings. The AI receives that state, realizes it needs broad up-to-the-minute web data and structured historical data, so it triggers a fan-out to a web agent and a Wikipedia agent at the exact same time. Once both agents finish, it fans in, combining all that rich research to generate a highly accurate, hallucination-free final answer.
Under the hood, this graph is working magic. It seamlessly coordinates pulling up to 3 results from the web using the Tavili API and grabbing exactly 2 documents from Wikipedia. And because we're using that custom reducer we just talked about, all of this raw, messy data coming from 5 different sources is neatly formatted into a super clean HTML context. By the time the final generate answer node fires off, the LLM is looking at a deeply verified, beautifully unified context prompt. It's just brilliant. And that right there illustrates the sheer power of advanced LangGraph. You are now armed with the command tool for truly edgeless routing, fan-out for lightning-fast parallel execution, and custom reducers for absolute control over your data. Your multi-agent workflows are practically limitless now. You aren't just coding rigid, hard-coded paths anymore. You are building genuinely intelligent, self-organizing systems. So the only question left to ask is, now that you have these tools, what are you going to build first? Thanks for joining me on this explainer, and I'll catch you on the next one.